All right, ladies and gentlemen, let's do another one. This one, we're going to be going over gravitation. Um, gravitation, it works pretty well with circular motion. However, it's distinct enough that I felt like kind of making its own set of slides, its own videos. But it's definitely going to be an application of what some of the stuff we've talked about when we went over circular motion. So if you haven't gone over circular motion yet, you're going to want to make sure you do that. Here is a video about gravity that I like. Recommend you check it out just to see. Maybe some of the stuff there will make more sense to you. But let's go ahead and get right into this. So first off, before we can launch into what gravitation is, we need to understand something called a vector field. All right. Now, we know what a vector is. A vector can be represented by an arrow that's pointing in the direction that something could be moving, or the direction that a force is being applied, or something like that. And that the size of that arrow helps us understand how big that vector is. All right. So when we talk about a vector field, we're talking about a continuous set of vectors. Whether it's acceleration or force, whatever the vectors are, a vector field is a continuous set of vectors and their size and direction at a given point in space. Okay, so it's an arrangement of a ton of vectors, where each vector in this field has a size and a direction, and it helps us to better understand what the value and direction of a single vector would be at a given point in time. And this will make a little more sense as we start to get into gravitation, all right? So the way we typically represent this is by a bunch of arrows whose size and direction help us to understand the magnitude and the direction of a given set of vectors at a point in space, okay? So if we look at this picture right here, this image, this is a good example of what a vector field could look like. Notice, it's a collection of arrows, and these arrows vary in size, they vary in direction. So you have some arrows over here that are large and pointing down and to the right. You have some arrows right here that are small and pointing up and to the right. So if I were at this point right here in the top left corner, if I wanted to know what vector would be there and how that would be, how objects would be interacting with this vector, I would see that the direction would be down and to the right, and that most likely what would happen is that there would be a strong effect right here. Versus if we kind of come towards the middle, the vector field is almost all but vanished at that point. And so there's not really, if there's an object right here, there's not going to be a lot of intense interaction with this the vector field. So the idea of a vector field, once again, is it helps us to get a feel for the size and direction of a variety of vectors. Well, same vector, but just at different points in space. All right. And objects tend to interact with vector fields. And the one that we're going to look at specifically would be how an object interacts, an object that has mass interacts with the gravitational field that exists, because a gravitational field is an example of a vector field. All right. Now, if you want to try and get a little more familiar with it, this simulation right here, this link right here, it runs a simulation that is a really good representation and example of vector fields. Okay, if this link doesn't work, which sometimes it does, sometimes it doesn't, this is another way that I have found it, is to go to Google, type in electric field hockey, and there's a one that says physics classroom. When I made the slides, it was the third link, and it's pretty much the same simulation or very similar to it. If you're looking at my slides and you look at the notes in my slides, I have the link to this website, different website in my notes. But both of these simulations, basically the same simulation, but they give you a really good feel for what a vector field actually is. Here's the other one once again. Okay. Now, in the simulation, it uses electric fields. We haven't talked about electric fields, but an electric field is a type of a vector field. Now, gravity is an attractive force, all right? And it can be represented by a vector field with arrows pointing towards the source of the gravitational field. All right. When we talk about electric fields, a negative charge does the same thing. The negative charge creates an electric field where the vectors in that field are all pointing towards the source or the negative charge. All right. So if you want to run this simulation with, oops, there we go. If you want to run this simulation with the with gravity in mind, try to do each level using only electric or using only negative charges. That's going to give you a good representation of what gravity could be like and how a mass might interact with that. Okay. All right, moving on. So gravity is a vector field. We call it the gravitational field. Now, the gravitational field, if you remember, I used the word attractive. Let's use a better word. It's centripetal. Okay. This shouldn't be the first time you've seen that word. We talked about it when I went over my uniform circular motion slides. Okay, gravitational field is centripetal. It is center seeking. So any object that has mass is going to interact with this gravitational field, and any object that has mass is going to cause a gravitational field. Okay, so an object has mass, it will generate its own gravitational field, and it will also interact with any other gravitational fields from other objects. Okay? Now, the gravitational field, we can figure this out by dividing the force of gravity by the mass. Okay? Now, if an object is in free fall, the acceleration at a given point in the gravitational field is going to be equal to this equation: force of gravity divided by mass. But once again, that's if the object is in free fall. Okay. If you want a good reminder of what free fall is and a good example of how even something like air can affect, with air resistance, how it can affect the fall of an object, this is a really good video where they drop a feather and a bowling ball in an environment where there's air, and then they create a vacuum where there's no air, and they do the same thing. You'll notice a very big difference, and you'll see why this concept of free fall can be very significant. So just if you're interested, that'd be a good thing to check out. All right. Now, keep in mind, the force of gravity is not the gravitational field. Okay. The gravitational field simply represents the acceleration due to gravity at a given point. Okay. We're not looking at the force of gravity here. We're looking at the acceleration due to gravity. Okay. Now, keep in mind, a force is an interaction between two or more objects. Okay. So the force of gravity requires two or more objects in order to even exist. All right. A gravitational field only needs the object that's creating it. It doesn't need another object to interact with in order to exist. All right. So you could have a planet in the middle of nowhere, out in the middle depths of space. There's no other objects around. There's no other gravitational fields or anything, and that object would still be generating a gravitational field. We won't really be able to see the effects of that gravitational field until a second object with mass interacts with it, but that field still exists. All right. Force of gravity, not so much. In order for there to be a force, there has to be two or more objects. All right. Now, the gravitational field is caused by anything that has mass. Now, typically in this situation, we're going to treat all masses as if they're a sphere and they're symmetric, evenly distributed. It makes our life a lot easier. Also, make sure you're familiar with the word, with the phrase inversely proportional. Tells us about relationship between different variables. Okay, the gravitational field is going to be inversely proportional to the square of the radial distance. Okay, if something's inversely proportional, that means that they behave oppositely. So if you have, oh goodness, let's see, let's do this. So for example, let's say that we had y equals 1 over x. This is a good example of an inversely proportional relationship. If I increase the value of x, y gets smaller and smaller and smaller. So they do the opposites. As one increases, the other decreases. Or if x decreases, y gets bigger. All right? That's inversely proportional. And the gravitational field is inversely proportional. The other one to be familiar with is directly proportional, and that would be something like this. If x increases, so does y. They do the same thing, okay? However, we're not going to worry about that right now because gravitational field is inversely proportional, okay? Specifically inversely proportional to the square of the radial distance, okay? Now, here's your equation. This is the equation to calculate the gravitation, to calculate the acceleration at a given point within a gravitational field for an object of mass m, okay? Now, this big capital G is something new. This is the universal gravitational constant. It is not a variable. It is not a variable. It is just this big number right down here. Now, because it's such a big number and a pain to write, we usually just use a capital G until we have to put the numbers into a calculator or something like that. Then we'll worry about it. Otherwise, it's a constant. It's like pi. The letter or the symbol pi. Pi means 3.1415, blah 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 blah, and it goes on forever. But I don't want to write the numbers to forever, so I just use the symbol pi to represent the number. Same thing here. Capital G has a very specific meaning in physics. Don't use a capital G unless you're referring to the universal gravitational constant, okay? This capital M, this mass, this is the mass that is causing the gravitational field. If you have a different object that's interacting with the field, that's great, but that's not what this mass is, okay? So let's say you have a satellite that's orbiting the Earth. Earth causes, the mass of Earth causes a gravitational field. So in this case, the mass here would be the mass of the Earth, not the mass of a satellite, okay? So it's the mass that's causing the field, and then R is what we call the radial distance. It's from the center of mass of the object causing it to whatever point in space we're looking at, okay? So, oh, I just boiled it. Whoops. What does R represent? Quick, try to remember. It's the radial distance, okay? Now, typically we assume it's the radius because we've used R for radius before, but technically it's the radial distance, okay? Once again, the radial distance is the distance between the center of mass for the mass causing the gravitational field and the point in question. Sometimes it's the center of mass of a second object or something like that, okay? Once again, G is not a variable. Keep that in mind. So the acceleration of gravity right here, the acceleration due to the gravitational field of an object that's interacting with it depends on what two variables? Let me say that again. That was confusing. The acceleration due to gravity in a gravitational field is dependent upon what two variables? Well, since G is not a variable, it's a constant, it depends only on the mass causing the gravitational field and the radial distance. All right? Those are the only two variables that affect the acceleration due to gravity within a gravitational field. All right? Now, true or false? The acceleration due to the force of gravity experienced by your head is different than the acceleration due to gravity experienced by your feet. Is that true or is that false? Okay, technically, it's true. Technically, it's true. The acceleration due to gravity experienced by your feet is a little bit stronger than the acceleration due to gravity experienced by your head. So technically, this is true. However, practically, it's false. The difference in that acceleration is so incredibly small that we basically treat it as the same thing. But if you think about it, your head has a larger radial distance from the center of Earth's mass than your feet does. And so because it has a larger radial distance, it has a smaller acceleration due to gravity. But once again, that difference in the radial distance is so small that the difference in acceleration is insignificant. So let's look at an example of this, all right? Mount Everest is right around 9,000 meters above sea level. Vegas, right around 600 meters above sea level. I want you to calculate the difference in the acceleration due to gravity between Mount Everest, and Las Vegas. So to do this, you first have to calculate what the acceleration due to gravity is at Mount Everest, top of Mount Everest, and then calculate the acceleration due to gravity in Las Vegas. Once you get those two numbers, subtract them. You're also going to need to look up the radius of the Earth and the mass of the Earth. When you look up the radius of the Earth, make sure that you use the radius of the Earth in meters, not miles, not kilometers, meters. When you're looking up the mass of the Earth, make sure that you're looking at the mass in kilograms. Okay? Go ahead and pause, do some calculations, and then keep playing when you're ready to go through it. All right. So this is the acceleration due to gravity at the top of Mount Everest. It's about 9.79 meters per second squared. Okay. I put everything into the equation right up here. This is the equation we start with. Then I put everything into the equation. All right. So that's Mount Everest. Let's look at Las Vegas. Okay. The acceleration due to gravity at Las Vegas, 9.81 meters per second squared. That should look familiar. That's what I've always told you to use, and often I tell you just to round it to 10, okay? But here we're trying to be specific, so 9.81 meters per second squared, all right? So if we subtract the two, the difference in the acceleration due to gravity between Mount Everest, which is really tall, just so you know, and Las Vegas is only 0.02 meters per second squared. That is such a small difference. No wonder the difference in acceleration between our feet and our head is insignificant. This one's already pretty small, and it's a pretty big distance. All right? Ladies and gentlemen, in order to see a big difference between significant difference or change in the acceleration due to gravity, you need a significant change or difference in the radial difference. Significant. It has to be very large. Otherwise, you're not going to get very big changes in the acceleration. All right? So let's look at a different example. All right? The International Space Station. Now we're looking at 400,000 meters above sea level. Okay? 400,000 meters above sea level. Okay? What is the acceleration due to gravity experienced by the International Space Station? Do some calculations, figure it out. All right, here you go. 8.69. All right, now it's starting to make a decent difference. This is over 1 meter per second squared, smaller than here in Las Vegas. One thing I will point out, I didn't point it out in the other ones, but I'm going to point it out right here. Okay, notice our radial distance includes the radius of the Earth and the height above the Earth. In this case, the radial distance includes the radius and the height above. You add them together and then you square that total sum. All right? Keep that in mind. So, anyhow, International Space Station still isn't as far away as the moon or the sun or anything like that, but it's significantly farther away than Las Vegas is or than even Mount Everest. And so we start to see a bigger change in the acceleration. All right? Okay. Now, the force of gravity describes the interaction that one mass has with another object that has mass. To be more specific, it describes the interaction between the mass of an object with the gravitational field of the mass of another object. Okay? Now, let's talk about direction. The acceleration due to gravity is always centripetal. So once again, what direction do you think the force of gravity is? If the acceleration due to gravity is always centripetal or center-seeking, what do you think the direction of the force of gravity would be? Well, it's also going to be centripetal. All right? I know we've always described it as down, but that only works for small scales. Once you get to the size of the planet, it suddenly gets a little bit harder to say down, because what's down for one side of the planet could be different for the other side of the planet. Okay, so we just will often say centripetal. All right. Now, the force of gravity works at all distances and scales. However, once we get to large scales between the Earth and the International Space Station, the Earth and the Moon, or the planets and the Sun, the force of gravity becomes the dominant force, and it starts to dominate all the other types of forces. All right. So let's go to the next slide. This is the equation for the force of gravity. Okay, this is the equation for the force of gravity. All right, part of it should look familiar. This is why. So first off, we started with the weight of an object, or the force of gravity. Force of gravity equals the mass of an object times the acceleration due to gravity. Traditionally, we've always just used 9.81 meters per second squared, or 10 meters per second squared. However, when we start talking about large scales, large distances, large radial distances, 9.81 or 10 meters per second squared will not work. And you have to resort to our acceleration due to gravity equation. We already went over this. So you're going to do a substitution. You substitute this equation in for little g, and you get the weight, or the force of gravity of an object. Okay, rather than call it weight, I like to call this the force of gravity equation. Okay, one thing I'll point out: big mass, little mass. Okay, it doesn't even have to be big mass, little mass. Just these two masses are not the same. Some people like to do M1 and M2. Some people do a capital M, a lowercase m. Some do mass A, mass B. It doesn't matter as long as you remember that these masses are different. One of these masses is causing a gravitational field. One of these masses is interacting with that gravitational field. All right? So let's say a person weighs 1,000 newtons. That's their force of gravity. 1,000 newtons at Las Vegas. What will happen to their weight if they were on top of Mount Everest? Also, what would happen to their weight if they were at sea level? You don't have to actually calculate it, but just use what we know about the equation and tell me what would happen to the weight of this person if they were suddenly in different locations. All right, well, let's look at our force of gravity equation. First off, the force of gravity is inversely proportional. Remember what that means. Inversely proportional to the radial distance, specifically to the square of the radial distance, just like the acceleration due to gravity. Therefore, as altitude, or the radial distance, increases, the force of gravity gets smaller. Likewise, as the altitude or radial distance decreases or gets smaller, then the force of gravity will increase. Therefore, if somebody who weighs 1,000 newtons suddenly goes to Mount Everest, they will weigh less at the top of Mount Everest. And if they were to go to sea level, they would weigh more at sea level. All right? Now, let's suppose that two objects attract each other with a force of 250 newtons. If the distance, radial distance between the two objects is doubled, what is the new force of attraction between the two objects? So think about this equation. All right? Now, if we doubled this radial distance, how is that going to affect the force of gravity? How would that affect our 250 newtons? Pause the video, see what you can come up with. All right. So, first off, keep in mind you can't just multiply this by 2. All right? If we're going to square the radial distance, that goes inside. We have to square the 2 as well. So, if we square the 2, then we get 4r squared. Well, if I have multiplied this side by 1/4, I have to multiply this side by 1/4. So by getting a 4 here, I have a 4 in my denominator here. Therefore, our force is going to be quartered. You're going to take this 250, divide it by 4, and that is the new force of attraction between the two objects. That's the new force of gravity between the two objects. Okay? Now, another question. The planet Jupiter is more than 300 times more massive than the Earth. Okay, and it has a radius that is 10 times larger. It's huge compared to the Earth. So we might expect that an object on the surface of Jupiter would weigh at least 300 times as much as it does on Earth. But actually, it barely weighs 3 times as much. Okay? Why is the weight difference, the difference in weight between the surface of Jupiter and the surface of Earth, why isn't it any bigger? I mean, Jupiter has 3 times more the mass, 10 times the radius. Why is an object not significantly more heavy on Jupiter? Well, the mass is bigger, but the radius is also bigger, and we have to square that radius. That increase in radius decreases the overall change in the force. It's just barely over 2.5 times larger. The force of gravity at the surface of Jupiter is barely over 2.5 times larger than it is on the surface of Earth, okay? And that's because this radius is 10 times larger and we're squaring it, all right? So, true or false? The International Space Station is not weightless. True or false? The acceleration due to Earth's gravity is not experienced by the International Space Station. Well, the first one is true and the second one is false. All right. The International Space Station still experiences the force of gravity. And to be honest, if you can answer this one correctly, it kind of gives you the answer to the next one. Because if the International Space Station, if an object still experiences the force of gravity, it's still experiencing the acceleration due to gravity. All right. If you're interested in how orbits work, this is a good video to watch. It explains how an object that's in orbit is still experiencing that force of gravity. And that even though we sometimes will describe an object as weightless when it's in orbit, it doesn't mean that there's no force of gravity. And this video is a good explanation of that. So if you're curious about that, check it out, okay? Also, if you're curious, this video right here describes how the force of gravity from the sun, from the moon, affects the tides on in Earth's bodies of water. So if you're interested in that, check that out as well. All right, let's relate this to uniform circular motion. That's what it's called. Okay, so what causes a mass to accelerate? Think about it. If a mass is accelerating, what causes it to accelerate? Well, a force. Anytime there's acceleration, there's a force causing that acceleration. All right, now, if you recall, this is Newton's second law for a centripetal force. For an object that's experiencing centripetal acceleration, this is Newton's second law. All right. It is, I go over this in my uniform circular motion video and slides, so go through those if you need a reminder, okay? But notice, the force is centripetal. It is center seeking. Now, what direction is the force of gravity? Well, like I've said, we've always described this as down, and on a small scale, when you're close to the surface of the planet of the Earth, that's true. However, what if you're looking at the Earth as a whole? On the North Pole, you might say that gravity is down. However, if you're on the South Pole, then it would seem like it's up. It's just very confusing to try and describe it when you're looking at the Earth as a whole. So, at a large scale, it's better to describe the force of gravity as centripetal. All right? Gravity is a centripetal force. All right. Now, we have, so we have our centripetal force equation is equal to the force, this centripetal mass equals velocity squared divided by r. And since gravity is a centripetal force, we can just say that the force of gravity is equal to this centripetal force right here, okay? This is useful because now we have two equations for the force of gravity. We have gravity expressed as a centripetal force right here, and then we have gravity being expressed by our traditional force of gravity equation right here, where we have two different masses and a radial distance up here as well. All right, so here's what I'd like you to do. Get out a blank piece of paper or something, set these two equations equal to each other because they are both f sub g. Set them equal to each other, and then solve for the velocity. The answer you get is going to be what we call the orbital velocity. All right. So orbital velocity, two different equations, set them equal to each other. All right. I'm not going to walk you through how to do each one, but I will point out a couple of things. Notice this r is going to cancel out the squared. There's still a radius right here, but this r cancels that out. This mass is the same as this mass, so they cancel each other out as well. Hopefully that helps to simplify how to get the answer, but this is what your orbital velocity is going to be. It's just the square root of your universal gravitational constant multiplied by the mass of the object causing the gravitational field divided by the radial distance. Okay? So let's look at a practice question. A lot of these practice questions, I'm not really going to go a lot into an explanation, but I will give you some answers. All right? You're going to have to apply what we've learned to not only get the answer, but to figure out why that's the right answer. That's part of the challenge. Okay? So a satellite travels around the sun in an elliptical orbit as shown. As the satellite travels from point X to point Y, which of the following is true about its speed? It increases, decreases, or stays the same. The correct answer is A. It will stay the same. Okay. A satellite of mass 3m and a speed v moves in a stable circular orbit. Stable means that it doesn't change, all right, around a planet of mass m. A second satellite of mass m and a speed 2v moves in a stable circular orbit around the same planet. Which satellite's orbit has the larger radius? Well, in this case, the larger mass will, all right? Because its velocity is smaller, that means it's going to have a larger radius, all right? Next. So, one object at the surface of the moon experiences the same gravitational force as the second object at the surface of Earth. Which of the following could be a reasonable conclusion? A, both objects fall with the same acceleration. B, both objects, or the object on the moon has the greater mass. C, object on Earth has the greater mass. Or D, both objects have identical masses. See what you can come up with. Okay, the correct answer is B. All right, the key here is that the gravitational forces are the same. So you can figure out, you can set the gravitational force of this object on the moon equal to the gravitational force of the object on Earth. And if you do that, using some logic, you can figure out that the answer is in fact B. All right. Two artificial satellites, satellite 1 and satellite 2, have circular orbits of radii r and 2r, respectively. That means that radii r goes with satellite 1 and radius 2r goes with satellite 2. And they are in circular orbits about the same planet. All right. The orbital velocity of satellite 1 is v. What is the orbital velocity of satellite 2? I want you to tell me in terms of v. It's equal to 1v, 2v, 3v, 4v, half v, quarter v, something like that, okay? The answer is v divided by the square root of 2. V divided by the square root of 2. All right. So first off, a little reminder, just because this is going to help us for one of the questions. This is slides from my uniform circular motion slides. So this is our regular definition of velocity. The distance it takes to travel one complete revolution. That distance is what we call the circumference. And then the time it takes to go one complete revolution is what we call the period. All right. So if we take our basic velocity equation, we replace displacement with circumference because they're both distances, both displacements. We replace time with period because they're both times. Then we're going to get velocity equals 2 pi r divided by t. This is our constant. This is a constant velocity of an object that's moving in a circle. All right. So if we combine this equation with our equation for centripetal acceleration, if we combine these two equations, then we get this right here. Okay. You simply take 2 pi r divided by t and input it into this right here. Replace our v. So you have to square everything right here. Once you do that, this is what you get. Okay? All right. It's going to be helpful. Hint, hint, wink, wink. Inside a washing machine, the radius of the cylinder where the clothes sit is 0.5 meters. One of its settings, the machine spins the cylinder at 2 revolutions per second. 2 revolutions per second. What is the acceleration of an item of clothing in the washing machine? Okay, let's see what you come up with. The correct answer is D. Okay. 2 stars, star A, star B, are in circular motion, or excuse me, are in circular orbits of radii RA and radii RB, respectively. Okay. And they are orbiting about their common center of mass point as shown. Please note that P is the center of mass. It is not an object. There is nothing at point P. It's simply the center of mass. All right. There are only 2 objects here, star A and star B. They're orbiting each other. Okay. So each star has the same period of revolution, which we're going to call capital T. I want you to determine expressions for the following 3 quantities that I will show you, and you're only allowed to have constants and these 3 variables in your answers to all of them. All right, so figure out an expression for the centripetal acceleration of star A. You can only have these variables and constants in your answer, so figure that out. After you figure that out, I want you to calculate, or I want you to determine an expression that will tell me what mass of star B is. And then I also want you to be able to give me an expression that tells me the mass of star A. Once again, you can only have these variables and then also constants in there. All right. So this one's difficult. It's going to require you to apply everything we've talked about. So pause the video, see what you can come up with. Okay, here are your answers. All right. This one is tricky. It's hard. If you didn't get it, that's okay. Here are the answers. Go back, start working through it. See if you can figure out how to get this. All right, for each one of these answers. Okay. All right, ladies and gentlemen, that wraps up this video for gravitation. If you have any questions, as always, please just let me know. And I will talk to you all later. Have a good one.